So my name is Moshe. I'll tell you just a few words about our company, and then we'll move to Yehiel. So just to let you know who we are RSIP Vision. Basically what we do is we develop algorithms in computer vision and deep learning. The company has been around for over 20 years, and we focus only on this aspect. So basically our clients come to us and say, we need a computer vision module, we have our product, we need to analyze some images or some videos or some point clouds or whatever, and we develop only the core algorithmic modules for these clients and deliver it to them. We're a growing company, especially over the last few years. We've reached over 45 engineers. Our main R&D center is actually here in Jerusalem. We have another one in Tel Aviv. And we have two other offices in these peripheral areas called Silicon Valley and Boston. But again, our main development is going on right here in Israel as we speak. Of course, a strong and experienced team, though I can't speak for myself. And our company has been over 20 years in the field. So we've really been with computer vision through all the developments and, of course, the recent revolutions over the past couple of years. And we work in a vast field of different applications because, as I said, if it's an image, if it's a video, if it's a point cloud, and we need to extract some interesting information, this is what we do. However, in recent years, we've been focusing more and more on the medical area. So I would say most of our projects, maybe the overwhelming majority of our projects, are in the medical field. And today we'll talk about surgical navigation. It's on the top row, third from the left, over there. And over the course of the years, we've developed dozens of solutions for many medical applications, from histopathology to segmentation and registration, which we'll talk about today, segmentation of lungs, for bronchoscopy navigation, cardiology, many projects in ophthalmology, etc. We also, as a leading company, we do some research collaborations with leading hospitals and universities. So it's not like here where there are research labs with a principal investigator, etc. Most of our efforts are devoted, of course, to commercial projects, but we do try to always have some collaboration going on with universities and hospitals, both here in Israel and overseas as well. We also publish a monthly newsletter called Computer Vision News. You can sign up, it's free. We cover the leading computer vision conferences such as MICAI, CVPR, ECCV. We've been there for a few years. We have the official daily newsletter. So it's sort of a way to get updated on the latest developments in computer vision without it's sort of in between the level of something you would read in a newspaper and something you would read in an academic paper. So it goes deeper than just the superficial level, but it's a way to get the intuition and ideas of these new developments in a relatively quick and user-friendly manner. And yeah, that's it. So I'm going to pass on the microphone to Yehiel.
Okay, so I'm going to talk about a navigation system for spine surgery, how we can build a navigation system, and their different components. I'm going to start talking, and then Moshe is going to continue on. So the outline of this lecture is going to be why you need to use a navigation system. Afterwards, let's define the problems that we have. I'm going to talk about registration, about X-ray calibration. Also, I'm going to show how you can create a digitally reconstruction radiograph, something called DRR. I'm going to go into it, and then I'm going to talk about the 2D, 3D registration process, both its initialization process and different optimization approaches, and then I'm going to summarize. If you have any questions, feel free to ask, no problem. What are the advantages of a navigation system? So there are several advantages. First of all, you want high accuracy. When a surgeon starts to work, you want him to be very accurate, especially for spine surgeries. There are very dangerous places in our spine that you don't want him to touch. So this is something important. Minimal invasion. Today, spine surgery, the surgeon cuts the patient. Okay. We want him to cut a very long cut he's doing in the back, and we want to make it as small as possible with minimal invasion. Low radiation, especially for the surgeon actually. because it's one of the problems of the surgeon during the process. They are doing several X-ray images, and for them, it's for a long time it's exposure. Both they can get cancer and also cataract. So it's very important to keep as low radiation as possible, and also for planning purposes. Before the operation, you can plan what's going to be the size of the screws that you want to place into the patient, the exact direction you want to go into. So this is very important. What is navigation system? So in 2D navigation, everyone knows, I assume you have a GPS, you have a 2D street map, and you would need to know what is the location of the car in your map. For example, here is a car, and now once I can place the car on the map, now we can start driving and continue following our car. In 3D navigation, it's the same, but now we have another dimension. So if before we talked about a two-dimensional street map, now I'm talking about a three-dimensional CT scan of the spine. This is our map. And instead of car, now we have the location of medical devices in the scan, if it's going to be a screwdriver or something else that the surgeon is using. And now we want to follow its location. So we have our tools, and now we are moving them around, and we want to see a full 3D map and to understand precisely where is our screwdrivers or other tools are located. So this is the purpose of our work. So let's do a short overview about all the models we have. So first of all, we'll need to have a calibration of X-ray camera. In the operation room, there is an X-ray camera. It's also called C-arm because of its looking like a big C. And we need to calibrate the X-ray camera. We need to say, once we have a 2D image, we want to have its segmentation. We want to find where is the location of each vertebra. Afterwards, there's also a module, which I'm going to talk a bit more, continue on, registration of a 2D image into a 3D image to find the connection between a 3D image, which is a CT, to the 2D image, which is the X-ray. We want to perform segmentation of the 3D image. This is something that Moshe will talk in the second lecture more in depth, how we can perform this segmentation. We want to find the location of all the tools in the operation room. This is also very important to have our navigation system. And besides this, also visualization. It's also important. Although after we have all the parts located in the correct place, we want to have a good way to visualize them for the surgeon to understand where is the location of his tools in this process. Okay, and as I said, we're going to concentrate in this lecture mainly on the registration of the 2D image to the 3D image. What is a CT scan or a 3D image? Just to be clear about it. So CT, it's a computated tomography scan. We are taking many X-ray scans from different angles, and then we can produce a 3D model of the object we just captured. The output of the CT, it's a 3D image. So each, what we call voxel, it's a volume pixel, represent the annotation of the tissue to X-ray radiation. There's units, it's a Hounsfield scale, but basically, so we have now a 3D object, X, Y, Z, and for each point in this object, we know how it is, how it's an attenuation for X-ray radiation, and this is how we create our CT scan. So this is one object we need to have. Another thing that I just will present, we are not working at something that we are using just from the shelf. It's a location of tools. We are using object IR tracking. There are companies that just can sell you these components. You have a camera here, and this camera, it's a IR camera, and we have a kind of a flags that have 4 trackers points that we can track them and find their location in the 3D image, and then we can find their both the translation and orientation of each one of them. You can talk about different coordinate systems. So we have a coordinate system of the camera and also the coordinate system of the object we are tracking in this case. So this is something you just get it from the shelf. You can place each tool in the operation room and put on it this flag, and now I know the exact location of this part. So what is the purpose of the registration? So we want to find the connection between CT scan. This CT scan was done, let's say, a week, 2 weeks ago. The patient came, performed this CT scan, and now we want to connect between the map that we already have of the patient spine to the tools that we have in the operation room. So the tools, you have your set of tools. Also, the X-ray is very important. Also on the X-ray, which is located in the operation room, there is these flags. Soon we're going to see why it's helping us. And now what we're going to do, we're going to use the X-ray image that we are taking in the operation room to connect between the CT scan and the tracking. So if you can see here, I have an X-ray. I can place on the X-ray the CT scan. Soon I'm going to explain a bit more what we are doing here, but this is how to connect between these two images. No questions? Let's continue on. So registration or image registration. So basically a 2D image registration is something that is simple to understand. So we have, let's say, one image, second image, and now we want to find a transformation. Can be translation, can be rotation, can be scaling sometime, and to find the connection between these two images. But now in our case, we want to find kind of a different connection. We want to find what we call the 2D, 3D registration. So we have a 3D object, which is our CT. It's a vertebra CT. And we have also the X-ray, which is a 2D image. And now we want to find the connection between these two objects. This is what we are looking for. So what is the way to do it? So there are two ways to connect between these objects. The first one, we want to map the 3D object into a 2D image. It's soon I'm going to talk about it. It's using a digital DRR, digitally reconstructed radiograph. I'm using this CT, and now I'm finding a way how to map it into a 2D image, which is similar to an X-ray. This is one way I can connect the 3D image, 3D object, to the 2D image. The different way around is if I have two or more images, I can create a 3D image. It's called object reconstruction, or if I'm just talking about a single point, it's going to be triangulation. And this is how I'm connecting between these two different objects. Yeah.
Why do you need to connect? The CT does not include all the information. Like the CT is composed of many X-ray images that are like a 3D.
Yeah, the CT have all the information. Yes. The CT is our map for the navigation system. But now I'm placing the patient in the operation room, and I need to find what is the relation between the patient and the tools that I have. I need to find a way to connect between the coordinate system of the CT to the coordinate system of the tools in the operation room. So the way I'm doing it, I'm using the X-ray. The X-ray, it's part of the operation room. It has on it the tracking flag. And now I'm going to show it. I'm going to take an X-ray image. And now I want to connect between the X-ray image and the CT scan. This way I can connect between the two different coordinate systems. Clear?
Sorry to interrupt.
Yeah.
In my hospital, we do the scan in the operating room. We do the CAT scan in the do you mean you do not do the CAT scan in your operating room?
No, the CT scan is done a week before the operation. you don't want to do a CT scan in the operation room. It's a long procedure and there's no real need for this. While a C-arm X-ray image is quite simple. You have it in the operation room. It's very short. So, yeah.
Do you keep photography using X-ray photography all the time?
You try not to do it. There are some for the patient and more important for the surgeon, because he's doing this procedure several times a day, could be, and you don't want to expose him to much radiation. So you try to do as limited exposures as possible. This is one of the reasons that we are trying to do this navigation system to reduce the radiation that the surgeon is exposed to.
But you said that you still need X-ray to get...
Yeah, but if I'm going to perform 2 X-ray images, it's not high dose. If you are doing it all the time... No, just for the beginning, just for the registration, and that's it.
And there isn't any movement or changes in...
If there is movement, so they will need to perform again this registration process. But basically, we are doing once this registration process, and then everything should work accurately.
What's the accuracy of the scan itself?
Now, it depends. X-ray can be very accurate. It can be 0.2 millimeters. And it's much more than you need for tools in the operation room. The CT depends on what accuracy you are working. There are, let's say, also 0.3 millimeters, something like this, 0.5. Depends on which tool you are using. So I'm going to talk about X-ray calibration. If you are familiar with, basically X-ray, it's like a pinhole camera. So I have an object, there is a small pinhole here, or here it's just the same, and now you can see it here. This is the image plane, and you can see it. X-ray is more or less the same, but with one main difference. As you can see here, you don't have this, that the image is upside down here, because what we have here is this. Our X-ray source is just the focal point here, so that we have it, and we're placing the object here, and it is there then mapped on the image. As you can see here, we have here this the X-ray source. Here we place the object, and then it is mapped on the image itself. So this is how we perform X-ray calibration, and you can describe it mathematically with using 2 matrices. The first one, we call it the external matrix M, which performs a transformation between the world coordinate system into the camera coordinate system. And the second matrix is K, the inner matrix, which is mapping from our 3D world into the 2D image. So you can write it down like this. So we have M, you have it's a 3x3 rotation matrix and a translation 3 parameters. And for the internal parameters, so they have the focus of the camera. You have fx and fy if it's not the same. You have the image center and skew, which is usually we don't use it. That says if the axes are orthogonal or not. But this is a model for the X-ray calibration. So if we are talking about 2D, 3D registration, so we want to use triangulation to find the starting point between the 2 images. So now we can ask the user just to, after he performs these 2 X-ray images at 2 different angles, what you see here, to place to where is the center of the vertebra that you want to work on, and now we can find its location in the 3D. So it's going to look something like this. So here we have 2 C-arm tools. Each one has a different image on it. And now once we have the X-ray, we have the projection matrix, and we can now perform initialize registration between the 2 different coordinate system, the coordinate system of the CT and the coordinate system of the X-ray, which is connected to the coordinate system of the world, which is the operation room. So this is a way we connect between the two different coordinate system. Another part we need to understand here is, okay, this is what we call, I talked before, it's DRR, digitally reconstructing the radiograph. So now I'm able to take the CT scan and to find how an X-ray gonna look if I'm gonna take a picture from a specific angle and direction. So we need to give to the to our algorithm, we need to the CT scan, the camera position and orientation, which we know from the X-ray. So I'm trying now to create an X-ray as similar as possible to the ones that we actually got in the operation room, and this is the way we will connect between the two objects. So we have a real X-ray that we know its exact location and orientation in which it was taken, and now we want to find the way to create it using our CT scan. So actually this is a bit computational, it's a bit complicated because now we need to sum for each ray that we have. We are summing all the points in this ray, and then we can create our new 2D image. We need to find a way to do it efficiently, but this is something that we need to do. Let's continue on. So we are talking about we need 3D segmentation. As I said, Moshe will explain how to do this segmentation, but this is important to perform all the registration on a single vertebra and not on all the spine together. The reason for this is because when you are doing the CT scan, it was 2 weeks ago. Since then, maybe your spine was in different location, and we know that one vertebra can move relative to the other vertebra, and we don't want to do a registration of all the spine because perhaps it moved. So what we are doing is a registration on a single vertebra. This is the way we are doing it. And now we need to define a cost function for our optimization process that we will start now. So a cost function that will compare between the DRR and the X-ray. There are several choices how we can choose this cost function. It's going to be a correlation between the images, gradient correlation, mutual information. There are many options that we can choose from how to find the best way to compare between these two different images. And as you can see, we can talk about bad matching, as you can see they're up, and the good matching here, where the gray is the X-ray image, the red is the DRR image. And now this is a way we're looking a way to find the best location for the CT to create this DRR, which is going to be as similar as possible to the X-ray. Yeah.
How can you be certain that the spine is in the same position it was when you took the CT?
It's not in the same position. Now I want to connect between the spine that was 2 weeks ago. We performed the.
It will be the same spine, but it will be maybe a bit tilted. Or
Exactly. This is why we are doing it on a single vertebra and not on all the spine together. As you can see, I'm performing here. This is the reason for the segmentation.
For each one of the.
Yeah. The surgeon wants to work on a specific vertebra, so this is a vertebra he's going to perform the registration on it. And on this it's going to work. For the other vertebra, it's not going to be accurate. And then if he wants to work on a different vertebra, so he needs also to perform the registration on the next vertebra.
Okay.
Yeah.
Could you please explain what's the difference between good and bad matching? Just the positioning of that vertebra? Or like
Yeah, as you can see, I hope you can see it here in this resolution, but you can see that this is the X-ray that we have. This is the background, and the red part is the DRR, the projection. So I'm projecting the CT on the X-ray, and as you can see, the lines here the lines are exactly the same. It's the X-ray, the CT is sitting exactly on the place that we would like to see it, and here it's just, you can see it to the right and upper, and there's also some a bit orientation differences between them.
Right, but is there like a machine that decides what's a good and what's a bad
Yeah,
match?
it's their optimization process that now we're going to go into it. So how we can perform this optimization process? So exactly what, good question. So I have these two CRM images, and now I'm kind of playing with the vertebra to find where is the exact location to place it, that we're going to see a good match in all the images that we have. We can have 2 images, we can have 3 or 4 images, and we want to find the best location to place this vertebra. What? Excuse me?
The model, you're working with changing the model itself.
Yeah, the city. This is the city, and I'm finding the best location for the city that it will project on the X-ray as accurate as possible. Okay, and now
Scale it sometimes?
What?
Will you scale it, make it bigger or smaller?
No, we don't. We're not. You can do for all the process scaling just for to expedite the process if you want to change the resolution. But the scaling here is very important. You need to keep the scaling because this is real object. This you have your objects at its size in millimeters or few centimeters here.
So if this model is smaller than what you see in real life because the camera was further away or closer.
So we need to find what we know the location of the cameras. These are the 2 cameras I have. I know their exact location from the tracking system I have. And now I did initialization, which placed the vertebra more or less. I know it's here in this area, and now I need to perform the optimization to find the exact location of this vertebra. For the optimization, we have here 6 degrees of freedom here in this problem. So we have 3 degrees of freedom, which are translation, and another 3 degrees of freedom, which are rotation. So for translation, it's quite simple. Usually it's in millimeters, and we know how to use it. For the orientations, there are several different ways how to handle orientation. Each one has its pros and cons. Rotation matrix, it has 9 parameters, but it has 6 constraints because actually we have here only 3 degrees of freedom. It's quite easy to understand, and it's very working quite well, but for optimization process, it's not going to be a good way to work. Euler angles, if you're familiar with, it's 3 parameters, but it has some non-smooth points that it's not injective. It has gimbal. It's places that it has more than one answer how to create these 3 parameters. You can use quaternion, which are 4 parameters with a single constraint. It's smooth, it's fast to compute, but still we have a constraint. Axis angle, it's 3 parameters. There are some problems there, but it's from all the options here, it's going to be the best to use. But once we have it, now we have a 6 degree of freedom space, and now we want to start an optimization process. So there are 2 different methods we can use. The first one is called CMAES. It's Covariance Matrix Adaptation Evolution Strategy, which means it's kind of working in different generations. So I have the covariance matrix, which is how the distribution of the points will look in all the space. And now I'm starting to work on it. I'm starting with first generation. I have, let's say I'm deciding I have 20 points each generation. So I have 20 points here, maybe more, I didn't count. And this is how they distribute. And now, after the first generation, and now I can find what is the new covariance matrix I have and what is the new center I have. And then I can continue on to the next step and the next step. And generation by generation, I'm going to work until all the points will concentrate into the minimal of the functions that I'm looking for to optimize. So this is one optimization way that we can work. The other optimization process is gradient descent. I think this is a bit more familiar way. So again, we have it's step by step. I'm finding the gradient of the function, and then I'm going each time another step that goes towards the minimal of the function. and this is the way I can find the optimum we are looking for. So there are two different optimization processes. Each one has its differences. So let's see a short table. What are the differences? So the CMAS is it's quite long. It's working very slow because you need to a high number of cost evaluations versus the gradient descent, which is much faster. The advantage of the CMAS, it is not deterministic, and this way you will not fall into local minima sometimes. It can improve the optimization, so it can avoid local minima and gradient descent. If there is local minima, it's just going to fall down there, and you're going to get stuck there. There's no way to get out. The parameters, both of them don't have a large number of parameters. For the CMAS, it's just the size of the samples in the generation. For the gradient descent, mainly it's the size of the step size. Both of them can handle a large number of free parameter. And for accuracy, the CMAS is medium. The gradient descent is high, relatively. So the current implementation that we're working, we can start with the CMAS for a rough estimation of the optimization of the cost function, and then we continue on with the gradient descent to find a better result with high resolution. Once we performed all the optimization process, so we started in this position more or less. So we can see here, if you remember, the red is the DRR, the gray is the X-ray, and finally we can optimize both images, or it's going to be more than two images, to find the final location of the CT in the space.
It's the first initial
How do you get those?
This is, if you remember, I talked about triangulation, that the user points, say, okay, I have here a point, I have here a point, and now I can perform a triangulation because I know the projection properties of each axis, and then I can project them both. I say, okay, here is the initial location of the CT scan. It's not very accurate, but it's giving us a rough estimation of its location. So what we had here, so what I showed here is just how we can connect the X-ray into the CT by using DRR creation, using optimization. The second part, which I talked before, so we have an X-ray, we have the operation room coordinate system, and we showed how I'm using X-ray calibration and the tracking system to connect between these two spaces. And now I can connect them all together between the CT and the operation room tracking, which is what we looked for. We looked for how we can connect the CT scan to the operation room tracking, and this way navigation is working. That's it. Any questions? Yeah.
Each vertebra is different?
Yeah.
So you can't mix up and register?
You can mix up. This is why we need to ask the user, the surgeon in this case. He needs to say, okay, I want to perform the registration on this vertebra. He needs to place where it is. And also in the CT, also we need to choose which vertebra he's working on. Otherwise, it's not going to work.
But in 3D, each of them is different.
Yeah, each of them, as you go lower in the spine, it's a bit bigger than the previous one. Yeah. Yeah.
What do you calibrate the X-ray cameras with? Like what object?
What object? So it depends on what X-ray we have. So if it's in, you can place a kind of a calibration object that you're placing it once, you are looking on it, and then you can figure out what are the parameters. You know the exact size of this object, and now once you are performing single X-ray image, you can understand what is the exact calibration of the X-ray. This is one way. There are also other ways. Depends if we have all kind of different, there are some problems with X-ray, but basically this is the way we're doing it.
You said you take multiple images from
Yeah.
different direction. What's the size of the angle between the direction that you take for the
It's let's say 0 and 90. This is basically in addition to this, depends on, there are some limitations of the operation room. So it can be 25 degrees or something like this. Otherwise, it has some problems in the that you can't work with. Any other questions? Yeah.
What's the running time of your algorithm?
Let's say it can be a half a minute, something like this. I'm talking about the registration, something like this. It really depends on many parameters. Let's say something like this. Yeah.
Does some surgeon use it now?
Not yet. Not yet. There are parts that are used, but not the whole process. Yeah.
You asked the doctor at the beginning, after doing the 3D segmentation, you ask him which vertebrae he wants to work on.
Exactly.
So that's the first time the doctor looks at your image processing during the process, before the actual output.
Yeah.
So it's like expert supervision in that part. Do you have another part where he looks again?
Yeah, on the X-ray images, because he needs also here to tell me which vertebra he wants us to work on. Because also here I can't really know.
So he needs to both tag the 3D image and the 2D images. He looks at both.
Yeah, depends on what system, but yes, let's say this is basically what we ask for him.
So the entire setup, how long does it take? 10 minutes?
No. So let's say it's a half a minute, let's say, once everything is ready, which I mean the calibration is ready, the segmentation of the 3D is ready, so the optimization itself, it's half a minute.
Yeah, but all of the setup...
Now it depends, because segmentation you can perform not in real time, you can perform it beforehand, so it's... And this is also Moshe going to talk about, it maybe has better numbers, but I think it's several minutes. Yeah.
How do you constrain the human or the subject to stay in the same position? I mean, is it enough to make him sleep?
He's sleeping at this part. Otherwise, it's not going to be good.
It's painful enough, hasn't it?
Yeah.
The end result, is it a 2D, is it a 2D result or a 3D map?
The end result is a transformation matrix, a 3D transformation matrix. Rotation and translation. Okay, thank you very much.